All right, so welcome. So we are doing our exam 3 review because exam 3 is going to be Thursday in class, basically covering induction machines. All right, that's the focus of it. But as we discussed, almost all the calculations, because we're in 3-phase power, we have to figure out when to use line voltages, phase voltages, line currents, phase currents, when to use a square root of 3. We also have to be able to do AC circuit analysis. So using magnitude and phase angles and doing all those calculations, including impedances, and just being able to understand how to do power triangles, right? So, and it's kind of, it seems like we're being sneaky or tricky, but in actuality, this is a 3-phase AC circuit analysis. Just like you can do Thevenin's theorem or I don't know, superposition or whatever, you've been using or applying circuit analysis techniques that you learned prior to that, right? KVL, KCL, how to do loop equations. It's the same idea that we're doing here. It's just that you have to have more background information to be able to do AC circuit analysis and also to do 3-phase power, right? That's really, you know, what we're applying here. So all the calculations that we did at the beginning of the semester is sort of a little bit of primer review of AC circuits. And then we add on the concepts of 3-phase power. All right. So those topics will, or if you do work in the utility style industry, and actually one of your classmates had a question about, here's a 3-phase generator and the nameplate doesn't exactly match the calculations, but his calculations were correct. There just was a slight discrepancy with the nameplate. So it could be that, you know, it could be a rounding mistake. You know, they said 75, maybe it's 75.3. You know, I mean, it could have been off by something like that. There could be a whole host of reasons, but his calculations were correct. So that's the same idea. These calculations, if you're going to do this type of work, you have to follow and apply to anything that you have moving beyond. So the reason why I'm saying that is because all that stuff feeds into induction machines analysis, because an induction machine is just a 3-phase AC circuit with power, with magnitudes, with angles, with square roots of 3s, all that stuff. Okay. So at the beginning of the semester, remember when I said a lot of this stuff just builds, that's because you're just doing circuit analysis. If you remember when we looked at the induction machine equivalent circuit, we actually could have done the V Thevenin and R Thevenin and X Thevenin approach, or we could have just written loop equations, right, to do all our calculations. So all that stuff is stuff that you learned, loop equations you learned back in DC circuits, perhaps. So it's the same basic concepts we just keep applying over and over and over again. So we'll hit the highlights unless people have specific questions that they want to get into about 3-phase power or anything like that. Again, because we are heavily relying on those, it's important that you get good at that. And that's one of the things that the person who teaches the FE preparation course, that course, she said that there's some confusion about when to use a square root of 3 and when to use 3. Okay. So if you're still struggling with when to use that, then we can talk about that today. Or if you feel comfortable, we can proceed on. It really just depends on what you all have for questions. So should we just go on with the major topics here? And yes, sir. Sure.
You know, the power in Orno on Saturday.
So the question for TV land is, do you know what happens with the power on Saturday? There was about 2,000 customers, give or take, that lost power for, what was it, 6 hours? Almost the whole day. 4 p.m.
Something happened in the steam plant, right?
Hold on, what was that?
I said there was, I know there was like a bunch of fire trucks at the steam plant lot.
Say that one more time. We can't hear you.
Sorry, can you hear me now?
Yes.
I know there was a bunch of fire trucks at the steam plant. Was it something to do with that?
So were you on, do you live on campus or?
No, I was delivering pizza when I all like big persona like from the fire department shut down like the road going to Old Town by yeah. Oh, it's I lived on campus. I was trying to figure why there was so many fire trucks flying around that.
Okay. Transformer blew up and a pole fell down.
I heard transformers were popping like crazy.
Then if there was Persona trucks slowly making their way all the way up to like the college Ave, by like the bridge. So that one end.
Really? Because traditionally, when one piece of equipment fails, it should only affect that one piece of equipment, and then the system should be able to sustain. So depending on the size of that transformer, it could be that it was a voltage regulator and maybe it spiked high on the voltage and maybe they popped, they burned out devices that way. I haven't heard. So it sounds like just a car accident. And I would imagine that they took out a couple pieces of equipment, but maybe they broke the line and maybe it was a major feed line, because what feeds this area, there's a substation in Orono. I think it's over down by the hydro facility. Yeah, by the dam. So there's a small, they call it the Orono sub, and that feeds a bunch of distribution circuits. There's also a 46 kV line that runs on that road. So if they took out that pole, then that would make sense, because that would feed a lot of customers. And then they would have to refeed back through Milford. That's a big loop. It can come at power from both directions. So what I mean is normally we have a radial feed, which just goes out. A loop feed means it goes out, but then something else comes around and they come back to the same point. It's kind of like campus. Campus is the loop feed as well. Yeah, so it could be 2 3-phase lines, but generally speaking, if you have 2 3-phase lines, usually it's not the same voltage level. It would be a higher voltage and a lower voltage. So it could be that it was a 46 kV. Did campus lose power that day?
Yeah.
Okay.
Campus got their power. College Ave got their power back on, but then like the road by Park Street and like all that without power.
Yeah, so they must have taken down the 46 kV line. And then before they could refeed from Milford, which it should auto refeed, maybe there was just something that was a problem. They did have a problem with the switch at the top of campus that would prevent them from doing that, because it's supposed to, that 46 kV line should just, it's called not a recloser, but it's called a sectionalizer. Yeah, they have sectionalizers that can come around and they can reconfigure things. And so I'm wondering if something was set up with that, maybe that pole that went down must have the sectionalizer. So that's, there's an accident that took out a 46 kV line. And that's why it's a problem.
3 big voltage regulators, like where the police cars are on A3, but any kind of right for the Ave, we have a section with 3 big voltage regulators.
Yeah. So that if it was one of those poles, those 46 kV regulators, I mean, those regulators would probably not be on the 46 kV system. They're usually on distribution circuits. But again, it could have been, it's very common that you have an overhead pole or an overhead line that, that have 2 overhead lines that share a pole, just because you can't run 30 poles on the side of the road. It's just not practical. So it was probably took out a section of the 46 kV, and that's my best guess. They didn't make a big press announcement. They just said 2,000 customers, and yeah, but you can go to Europe and most of their stuff is underground. They don't have those same problems with accidents, but actually overhead lines are supposed to be more reliable for time, because that was a 6-hour outage, but they could replace it in 6 hours. But if that was underground and somehow something broke, it would take days for them to dig it up and get all the equipment and the repair stuff. Plus underground equipment is much more expensive and it's not easily stocked on a shelf. So underground stuff usually has a longer time out of service. You can make a way more robust system. It's just we'd have to pay more. Anybody here happy with what they pay for electricity rates? Nobody likes their electricity rates? Oh. How many people here that pay their electricity complain about their cell phone bill? Which one's more? Electricity is more than your cell phone bill? I think most people cell phone is at least 120 to 150 a month.
That's what my electric is.
My electric bill, and I have an electric plug-in car. Again, it's season dependent. I pay $100 for electricity. And my cell phone bill, my wife and I are on a shared plan. It's about 130 or 140. It's a pretty basic plan too. So I would say that's one of the cheaper cell phone plans. So anyway, just think about that next time you see your electricity bill and compare that to your cell phone bill. And, I know you get to watch TikTok videos and get loads of entertainment, but a lot of that stuff that you get on your cell phone is kind of eroding your brain. So yeah, that's the best that I know. bigger deals will be announced. You'll actually find stuff, but small stuff like that, you'll never find out on it. If it's a big thing that impacts multiple states, that usually comes out with a warning, and NERC does stuff and people get fines, and if something happens over here, you'll hear about it from the PUC. Because Versant has to go for a rate increase every year, it seems like. And the PUC could say, well, you don't meet reliability criteria, so they'll actually punish them and not let them get a rate increase. So they're incentivized to keep the power running, or else they don't get a rate increase. So although the state of Maine is trying to publicize, so all the generation and transmission would be owned by the state of Maine. It would be a public utility, not a private utility. So who knows if that passes or not? We'll see. You get to vote on that in the fall, I believe. Any other questions? Good discussion. All right, so induction machines, it has to operate at not synchronous speed. And if it's an induction motor, which is really what we focused on, we talked a little bit about induction generators, but they tend to be pretty small in comparison to the amount of induction motors that you'll actually find. I would say it's many orders of magnitude difference in between the two. So you have a concept of slip, which means your induction motor has to operate at less than synchronous speed. Okay. So if it's a 4-pole machine, it can't operate at 1800 RPM. It might get to 1799, but it can't operate at 1800 RPM. And the reason why it can't operate at 1800 RPM is because that rotating magnetic field. So when we talk about the flow of a class, we did a bunch of stuff at the beginning for fundamentals. Then we got into AC rotating magnetic waves. That's just a rotating magnetic wave because we have a set of 3-phase currents going through a set of windings. Those currents would go ahead and give you a synchronous speed magnetic field. And the magnetic field rotates at 1800 RPM, 3600 RPM, whatever the synchronous speed is, depending on the number of poles, right? So we know that as long as we have an AC waveform, three AC waveforms, so a 3-phase power supply going into a 3-phase set of windings, then the idea is that we're going to produce a rotating magnetic field at synchronous speed. So the only way we can induce a voltage and or a current on that rotor winding. So remember, that's the thing about an induction motor, that rotor field is induced. There's no physical connection between the stator and the rotor. Physical electrical connection is what I mean. Then you're going to go ahead and get a current flow on there. So you have a difference in speed, which means you're going to generate a voltage and a current on that rotor circuit. And the rotor circuit allows to have that current to flow because your rotor windings are short-circuited. So with our short-circuited windings, we get a current. That current is AC, and its frequency is going to be whatever it needs to be to make up the difference in speed, because that AC frequency that we have on the rotor is going to spin at whatever is going to cause a magnetic field to spin at whatever that equivalent synchronous speed is. And the difference in speed between actual mechanical speed and synchronous speed is the equivalent electrical frequency. Okay, so that's a long way of saying our rotor field rotates at the same speed as our stator field. Okay, so be very careful and listen to the terms I'm using. Rotor field and stator field rotate at the same speeds. I never said the rotor itself rotates at synchronous speed. We said that it has to rotate at less than synchronous speed. So the difference in speed between the actual mechanical rotation and here's the thing, either the rotor field or the stator field is the slip. That's the slip speed. So the slip speed is the actual difference. And we don't usually talk about slip speed. That's a lot less useful for us. We usually talk about the concept of slip. So our slip is going to be a ratio, right? Which is the slip speed divided by the synchronous speed. So that's what we have here. Our term slip, and it's really based on the slip speed is how we develop it. And then we just do it as a ratio. And it's useful to know that as a ratio because it tells us from 0% to 100% slip what the actual performance of our machine is going to be. It's less useful for us to actually know the slip speed. Do I really care what the actual slip is. All I care about is I want a motor that can put out 100 horsepower as efficiently as possible. So I don't really care if this is 5 or 500. I just want this percentage to be as low as possible so I can get as an efficient motor as possible. So slip is going to vary between 0 and 1. No slip or 0 means it is running at synchronous speed. And the only way it runs at synchronous speed is if something's pushing it, right? Because we have no current, we have no rotor magnetic field, so we don't have magnets either chasing each other or opposing each other to attract each other. So that's not going to work for us. So the only way that we get them to rotate at the same speed is something is rotating a hunk of metal. So if you want the two to operate in sync with each other, then you actually have to provide a small amount of input force to get those to spin at the same speed. Okay. And the reason why we do that is because we have losses. We have bearing losses. We have friction and windage losses. We have stray losses that we can't categorize. All those mechanical losses are what we have to do to apply an external torque to get that to rotate. But that's not usually a good design. That's not usually practical. Most mechanical loads, to the best of my knowledge, don't have the luxury of either exporting power or importing power, right? Like a pump wants to pump water, it's not going to run in the reverse direction. I mean, you can design them that way, but I think, and I'm not a pump designer, you can check with some of your mechanical friends, but most of the time pumps are optimized to work in one direction. They take water from here and they pump it up into this direction. It's not usual that they go in the opposite direction, but maybe, I don't know. I know like those pump storage facility I keep talking about in Western Massachusetts, that is the same design. It can pump water up the mountain, or it can take water in the opposite direction and run a generator. But I would imagine that's a pretty unique application. Same thing with an air compressor. You're not going to go ahead and rotate or get the air compressor to generate electricity, because that's not usually what we do. We want to optimize it for our mechanical output, not for our electrical output. That doesn't mean we can't use braking technology. So that's when we would use our electric motor, which is bidirectional and works either way. We can use our electrical device to either export or import, because sometimes we're pushing the wheels and sometimes we're trying to slow them down. Okay.
There are bidirectional heat pumps. If you want to have like AC that also works as a heater,
Okay.
but that's the only example I can think of.
So the bidirectional heat pump, it uses the same compressor to either increase or decrease pressure.
Yeah.
Okay.
Well, I think there's two.
To what?
No, you're right. Yeah.
I don't know. I've never looked at them. I thought it was a different device. I thought they had a compressor that would either run it as an air conditioner. I think it, and I always get this backwards, or they had a pressure, dropping system that would operate it in the opposite direction. So I thought they had two different devices, but
Well, they have to have both, because you have to compress it, and then there's heat exchange, and then you expand it again, and then there's heat exchange.
right.
And you can have a reversible cycle like that.
Okay. Yeah. So maybe the heat pump is a good example or an application. So with that being said, we have no slip or we have full slip for our induction motors. Full slip means it's locked in position. It's not rotating. And we'll look at why when something is under a locked or a blocked rotor condition, it's not going to live or last very long like that. So I think that summarizes everything. Our electrical frequency, we can determine what the actual speed or the actual frequency is by taking the input or the applied electrical frequency and multiplying that by slip, S times FE. Okay. Here's some examples, but keep in mind, don't just study those examples and expect you'll do perfect on the test, right? These are just some ideas to help you maybe fine tune your studying. Speed versus torque characteristics. We did this in lab and it's very useful because it tells us, or it validates a couple of things. It validates our equivalent circuit model, but it also tells us if you're a mechanical engineer and you're trying to drive or you're trying to use a motor in a particular application, you can see, is my motor going to be sufficient for the application that I'm trying to do? Now, You don't often see, and again, this is just very limited because I haven't specified a lot of motors where I've had to get into this level of detail, because again, who specifies the motors? It's usually, sounds crazy, but it's the mechanical engineers that usually specify the motors, because they're the ones who know what the load is going to be. So they know it needs to be 100 horsepower at 3200 RPM or whatever. They do all the calculations to figure that out. And you just come up with general design parameters as an electrical engineer saying, I want it to be able to run at a 1.15 service factor. I want the power factor to be a certain value, the electrical parameters, but the actual torque versus speed characteristic is more of a mechanical parameter. So the only time I've seen actual torque versus speed characteristics is at nuclear plants, where they have very detailed studies where they're looking at the speed and they're trying to figure out what happens with the pump and all these different things, because they're trying to calculate load. So those are the only times that I've actually seen them, but I'm sure they're available. And if we have these impedance data, we can actually come up with them ourselves. So our motor versus speed characteristics, we saw, and it usually was between a slip of 0 RPM, all the way up to a slip of 0, or whatever synchronous speed was going to be. And we saw, do I have the curve here? I don't have the curve. And we saw, I'll just draw one, that oftentimes it looks something like that, right? So that was our torque versus speed characteristic. We were usually operating way down over here because our slip, it's a very low slip, 1, 2, 3%. That's when our motor is operating at its highest level of efficiency. It has more output torque capability. So this is the full load value. Our pull-out value, this is maximum torque capability. It's well above the full load value, and that's okay, because we want to go ahead and make sure that our motor can start up and get up to speed, whatever mechanical thing is connected to it. If our full load torque was greater than our pull-out torque, then we'd have a motor stall condition, right? So we don't want that. What we want is we want our pull-out torque to be much, much higher than our full load torque. And even our starting torque, when the motor first is energized, our starting value should be greater than our full load torque. Now, it depends on the mechanical application, but a lot of pumping, there are some pumps that start, you're not pumping any water, so there's hardly any load on it. So it really just depends on the application and how the pump is designed. Do you need to have a lot of starting torque, or do you need very little? But the standard is to have, 2 to 3 times more what your full load torque can be. And then that's our characteristic. We start, we go to a maximum, and then we run at our full load value, which is a very low slip, again, to improve the efficiency of this particular machine. Can't run very long anywhere above the full load torque, because the full load torque, even though the torque or the power output might be lower, we're pulling in more current than that motor is designed for. So pulling in more than the nominal rating of current can be disastrous for the particular machine. All right. And all the protection that you see, and I can't remember who mentioned this class, but you can trip motors out on stalling. But if you run it under slight low overload conditions, 5 or 10%, the motor will do that as long as it can. But over time, it generates more and more heat until it has the potential to be damaged. Okay. So 5%, 10% is usually not an overload condition that the motor will trip out on. And the reason why you don't trip it out on 5 or 10% is because, is that really an overload, or is that just a mismeasurement? Remember, we have devices. So if you look at protection for devices, usually protection is for tripping of the device. So you have a lot of current going to it. You got a problem, we got to take that offline. But overload conditions is somebody put the wrong piece of equipment in there. You screwed up your design. That's up to the operator to go out and say, hey, that motor's getting pretty hot. We better protect it. We better go out and trip it. And small motors, I don't know if anybody's ever played with it, but small motors, like, I don't know, old electric drills or something like that, they used to have a little thermomechanical device that would trip, and you'd have to wait for it to cool. You just have to let it cool down. Like, anybody here dry their hair with a hair dryer? See, I got that problem, right? I got to dry my hair. But all you long-haired folks, get a blow dry your hair, and if you leave it on too long, sometimes it just stops, right? That's because it's just too hot inside. So it's the same concept in the motor. you can put devices that will prevent the unit from operating because the temperature is too high. Small motors, you do that. Large motors, they use things called thermal overloads, which are usually much tighter in tolerance and usually are adjustable, especially the ones today, which are all microprocessor based. You can get them to be exact if you want. But you still, if you're less than 5% over full load rating, you may want to rethink about the application. You should always have lots of margin between your motor. Remember what we talked about in this class, if you have a motor application that needs 9.73 horsepower, don't go out and buy 9.73 horsepower. First off, you can't find one. They don't exist unless you have one custom made. And secondly, it's okay to put a 10 horsepower motor. It just means it's going to run at a slightly higher than full load speed. So if it runs a little bit faster, as long as your application is designed so that it can handle higher speeds, it usually won't be a big deal. It'll pull out so that once the speed will match what the torque output is, then it reaches a steady state operation. And that should be less than the 10 horsepower that is the motor is rated for. Okay, if it runs at slower speed than nameplate, you got a problem. You got to go out and figure out why your application is spinning at less than full load speed. So for those of you who are going to design systems, and if your motor is running at lower than synchronous speed when you energize it, you should stop it and try to figure out what's going on. You got a problem. Something could be binding. One of the most common ones, and I don't know if people have done this, but if you've ever put a motor, most people probably haven't done this, but anybody here ever work on cars? You know what a shim is? What's the purpose of a shim? Yeah, usually it basically adjusts things sometimes to 1,000th of an inch, and it can move things up or down. And the idea is that the shafts for your mechanical and your motor aren't lined up, you know, even off by a degree, you can get something that wants to go this way and this one wants to go this way. You can put a lot of demand on both pieces of equipment. And so one of the things you do, at least for automotive, is you put shims sometimes to go ahead and make sure things line up as perfectly as possible. In motor applications, it's even more critical to make sure that those are lined up. So you actually have motor installers who don't just put a motor application on a pedestal and then walk away. Usually you buy it as a skid. Anybody know why you buy a skid assembly? Remember we talked about the mechanical engineers will buy the whole assembly, the pump and the motor, because it's put on it's purchased from us on a skid. And the reason why it's on a skid is that the factory, they'll make sure that it's all lined up. They have way more sophisticated pieces of equipment to install stuff than you do. But if you change out a motor, make sure you have the right capability to go ahead and shim it up to make sure, because that's a very common one. It's called binding, and it's because things aren't aligned. It doesn't have to be this way. It could be this way. You know, it could be any application, but that's typically when you'll see things that are running, and they might last for a little while, but over time, you'll damage your pieces of equipment. Okay. Yes, sir.
So from my experience, when you use it for like valve branches and stuff,
Mhm.
you could also like the thing you use like level out the motor as well.
Yeah, so if you pour, so normally what happens when you have a motor, right? You don't want to stick it right on the concrete floor. Usually you raise it up a couple inches, 3 inches, mainly because you don't want people walking into it. If water or something spills, you just want a little bit of I think they call them a housekeeping pad is the term that you would use. And why is it a housekeeping? Because if somebody's brooming along, right, you don't want them to just get stuff into the application. So you pour a housekeeping pad. And then sometimes what I've seen on the top, I've seen this for electrical, they'll actually buy an angle iron, a piece of angle iron, and they'll put that in the top of the concrete. And the whole purpose of that angle iron is so that should be a piece of angle iron. It should be perfectly smooth and straight. So when you embed that in the concrete, you have a nice flat plane to do stuff. Once you bolt things down, you still may need to shim it, depending on if the motor is correct. Sometimes there's a little bit, you know, because it's very difficult to get concrete to be perfectly smooth. So you'll literally just buy shims and then you'll put those under the feet and then you'll just shim it up or down as necessary. Yep. So very, very common. It's very difficult for the mechanics, not the auto mechanics, but you know, the mechanics that work at mills and all that stuff. They have a tough job. And electrically, I tell all people that, you know, everybody's petrified of doing electrical work, but it's so much easier. You don't have to worry about shims when you're running electrical. You're just like, hey, I'll wire up the motor. the junction box. It's spinning the wrong way. Okay, just swap two leads. As long as you train it down and it kind of looks okay, that's it. But the mechanicals, they have a much harder time. They have to worry about, alignments and stuff like that, that electrical engineers really don't need to worry all that much about. So we have it a lot easier. So, yeah, so questions on torque versus speed characteristics. That's the really important part for, there are a bunch of different characteristics. We had P and Q. We know it's an induction machine, which looks like an inductor and a resistor. So it's always going to have is it lagging or leading power factor? Let's see. So it's a throwback from earlier in the semester. Does an induction motor have a leading or lagging power factor?
Lagging.
Lagging? Anybody want to agree or say leading? How about a not sure? It's a really easy way to do that. You just ask your friend Eli. What do they say? I don't know about pronouns, so I'll just use they. Don't want to offend anybody, so. Say that again. Say it again.
Current lags the voltage.
Current. It's always what current's doing, right? There's no such thing as voltage leading. I'm trying to remove that from your brain because we remember, and I'm giving you a little bit of a hard time just to help you learn. It's always what is current doing, right? Current is either leading or lagging the voltage. We never think about it at voltage because you can easily get confused because the next time I said, hey, it's a leading power factor, you might say, oh, the voltage is leading the current. It's not that case. You know what I mean? So always think about what current is doing. And Eli says in an inductor that the current lags the voltage. So it is a lagging power factor. Okay. So regardless of how much power it's outputting, it'll always operate at a lagging power factor. And here's our equivalent circuit. Just like a transformer, except for the secondary winding is short circuited. That's all. Okay. So go back to our transformer. We have a resistor and inductor on this primary side. We have some core and some magnetizing. We have a resistor and an inductor on the secondary side. It's the same thing. So an induction motor is a rotating transformer. It operates on exactly the same principles as the transformer. You have a dpdt that drives a flux. That flux is linked on the other side, and you get a current. It's the same thing with the induction machine. What's interesting about this, because this can rotate, we have to somehow have this application modified so that we can express the speed of operation into our equivalent circuit. And then we do that right here. That's why that's R2 over S. It's not a fixed value. And we did a lot of perturbations to go ahead and get X2 and R2. Remember, we're trying to get everything onto the stator side because the turns ratio is going to vary. That can be a real pain in the keister. And actually measuring the rotor resistance and the rotor inductance is very difficult directly. So we reflect everything onto the primary or the stator winding. And I showed you, it's up to you, but I showed you this R2 over S. You could break this up into an R2 and an R2 times 1 minus S over S. If you do that, the R2 times 1 minus S over S is equivalent to the power that is converted to the mechanical realm. Okay, this is the combination of the two, and I included it here because it's easier to do circuit analysis with this. But if you wanted the full-blown Monty to go ahead and directly do calculations, it's better to divide this up into an R2 and an R2 times 1 minus S over S. Okay, those two are pretty helpful for you. The R2, again, is just the energy that is being lost in the form of heat on the rotor circuit because you have current flow, right? Anytime we have current, and we have resistance, we're gonna get some heat. R2 times 1 minus S is the power that is converted to mechanical power. Once we are in the rotor circuit and we get past our rotor resistance, all our power is going to be converted to mechanical power. I did this showing you how I would apply the KVL to do loop equations, and to do it this way, you're not required to do this, whatever's more comfortable with you. You may want to write down the Thevenin equivalent stuff, just because if I ask you for max torque, if you have those equations, it's all set for you. This one, you have to be able to interpolate data to figure out what the starting torque is, what the max torque is. If you have those two equivalent equation with Thevenin equivalencies, then you can just plug in the value of S equals what for my starting torque? What value of S do I need to substitute in to get starting torque? That's right, 1. Because the slip's equal to 1 when I have locked rotor conditions. If I want to get max torque, we know that our max torque is when we have max power transfer. So that's when our maximum power is going from our stator to our rotor. And we were able to develop that equation that way. So that will give you direct calculations. But if you want to do this approach with MATLAB, this is fine. Just don't magically provide answers. I need to see your work. So I would need to see your Thevenin stuff, either your Thevenin approach or your loop equations. And then you can say from MATLAB, I picked these points off the curve. That would be fine. Like I said, MATLAB's a calculator. It just makes the process a little easier. Yes, sir. The Thevenin one, I think I have it. Here. Sorry, I jumped ahead a little bit, but yes, they're on there. I knew I put them on there. Yes, sir.
How do you find current?
Sorry,
How do you find current?
how do I find current? What do you mean the current?
Like, without using the matrix, how do you find current using the current?
I don't know if I would, if I just want to find, let's go back to the circuit. If I just want to find stator current, I know I have to know what a value of slip is, and then I would just use loop equations to do that. I would solve for it that way. If I need to solve for the current. These equations over here, though, this is, I'm not looking for current. I'm looking for a torque at a specific speed or a specific slip. So I can use this equation. I want to figure out what the max torque is. So I first have to find out what the slip is at max torque. And then I substitute that in that equation. Okay. So one is trying to get you directly a torque, and the other one is just going to do the circuit analysis to get the results. Once you have your I1 and your I2, I don't have any torque at this point. Now what I need to do is I need to go through and get this power flow in an induction machine. I drop out stator core losses, stator copper losses. Core losses usually have to be provided unless somebody has given you R sub C, but you oftentimes don't have that, so you'll have to subtract it. Now we jump from the stator to the rotor. So that's our converted power from the stator to the rotor, not converted from electrical to mechanical. That jumps across the air gap. That's why we call it air gap. Now we take out our rotor copper losses. That's IR rotor currents, or I2 squared. If you look at the previous matrix, times R2, and now all power is converted. Then I subtract these, and now I have the output power, which then I can calculate torque. To the best of my knowledge, our mechanical engineering friends don't give a hoot about power output. They care about torque. Right? Any mechanical engineering friends want to say what they care about?
I mean, in my classes, I've had like asking about power, but I'm not sure in practical applications.
Torque.
Torque.
There you go.
Yeah, because power, it's like us, we electricals, right? We're always difficult because if you're in the real world, what is power? I mean, it doesn't do much for us. It's a capability, right? 100 horsepower motor is what it's capable of producing. That doesn't mean you're actually producing 100 horsepower. It means that you've got the capability to do 100 horsepower. It's a rating, it's a joules per second is a watt, right? But torque is, all right, I'm trying to get this lug nut off my tire. I'm putting a bunch of torque on it to get it to break free. So that's why and even as an electrical engineer, I find I use torque a lot more just in my own personal life. Because how many times have you looked at, anybody here get tires changed and you get aluminum wheels? How many times they tell you come back in 50 miles, so we'll retighten or retorque your lug nuts? You don't know about that?
Yeah.
Okay, a couple people said no. You may want to double check that. So every 50 miles, because aluminum is a soft metal, you're supposed to retorque them every 50 miles just to make sure it's safe. So if you haven't done that, but
You need to do the first time, then after that.
change your tires, right? Don't you?
Yeah, so you do have to change the tires. when you go 50.
Yeah, once you do 50, then you're good. Yeah. Until you change the tire or break it. Yes, that's correct. Yep. No, not every 50. You'd have a mechanic standing next to you the entire time. But yeah, torque is way more useful. I was doing something on a bicycle. My son's getting taller, so I had to adjust the seat height, and on it says no more than 8 Newton meters. So you see them all in your personal life all the time. So we live in the real world, and torque is a way more important application than power. Until how many horsepower does your car have, right? Which is actually a way less useful indicator than how much torque it can produce. Anybody here own a diesel vehicle? 400 horsepower, but it puts out 1,000 foot-pounds of torque. Very big difference that a 400 horsepower car versus that. So same thing with an electric one. So anyway,
Question on some terminology, Paul.
Yeah.
Homework 5, you asked for like developed torque and output torque and developed power and output power. Where I didn't see it in here. So which one of them is the developed torque versus
right
output?
here. This is developed torque. This is all the torque that is developed from the conversion from electrical world to mechanical world. The reason why it's not output torque and it's developed torque is because all these mechanical losses I've got to take out. So that's why the developed torque is what it actually is producing. But then in the mechanical world, we just have torque losses that we have to account for before we get to output. So converted or developed is the same thing.
Okay, so and torque induced is the developed torque,
Yep.
like in homework. Okay, thank you.
Yep. Does anybody know why we call it torque induced? It's a really important concept to call it torque induced.
Because you're inducing a magnetic field and the torque.
Not a magnetic field per se, but it's easier to think about in terms of generator. What if I'm a generator owner and I'm old school and I'm shoveling coal into my boiler to get steam, right? I keep shoveling it in, I can have a hotter furnace and I can produce more heat, which means I can produce more steam. And so that generator wants to spin at whatever synchronous speed is. So 1800 RPM, but I'm continuing to put more steam in. So, or more heat in, or more energy in, I can get more steam. How do I keep that turbine from overspinning? Well, I want to go higher than 1800 RPM because the induced torque has to match out the applied torque. That's when you don't continue to increase in speed. Okay. A better example is you're riding a bicycle and you're riding and pedaling as fast as you can, and you're in your tuck position, you're trying to go as fast as you can. And at some point, you just can't pedal any faster. That's because your applied torque, you're pedaling it your butt off, and the wind resistance plus the road resistance, and plus any increases in speed you're getting, those are the same. So when you reach torque balance, that's when you don't continue to increase in speed. So that's why it's induced torque, because your induced torque has to cancel out your applied torque. Otherwise, you haven't reached a stable operating point. Your speed continues to increase. So induced torque from an electrical standpoint, again, and this is an electrical class, that's why we try to use terminology that's more helpful for us to understand what's happening from an electrical perspective. But that induced torque is from the electrical power that is supplied. Does that make sense, Nate? Hopefully that does. Okay, so bunch of equations. Sorry, these are all over the place, but equation editor was giving me all kinds of problems getting things lined up. And I don't know why it was giving me such heartburn, but all these equations are just they're almost all derived or taken from here. These two are the same, right? Square root of 3 versus 3. I added that in here because of what our instructor was saying for EET 405. Stator copper losses, we have to go back to the equivalent circuit. That's the stator current squared times R1. Notice I'm not including magnitude because right now you guys are pros at calculating magnitude, calculating power losses. So I don't even need to put the magnitude signs up, right? You just know that this is the magnitude of the current. Air gap power. This is the simplified one. But remember, that's the power that's on the rotor circuit. So I go back to my equivalent circuit, all the power that is the real power that is consumed in the rotor circuit is determined from here. Rotor copper losses, here's the converted power. Those two again are from our equivalent circuit. And then our output, now we have to get in the mechanical world because our mechanical engineering friends, they have a much harder time telling us what the friction and windage and stray losses are, primarily because those are not linear. Friction and windage losses tend to be non-linear. It's speed dependent, but it's not just a one-for-one, not like resistors where we have a linear relationship. And that's our output power. Notice we have a bunch of threes here. That's because we're only dealing with a single phase equivalent. So we don't have a three-phase equivalent circuit. We know that we have three individual phases connected in wire delta to give us that. So other than here, everything else uses 3. Because the only time we use the square root of 3 is when we're dealing with phasors, voltage and current. Everything else does with 3, except we're getting sneaky over here because we're substituting in line quantities. And so that's why we have to use the square root of 3 over here. The actual equation is this. We just use the square root of 3 because we substituted in V line and I line. We substituted in some phasor quantities. And this first equation in your professional careers, this equation is much easier and more effective to use than this equation. Okay. And then this just shows you for every unit of air gap power, I use S, I lose S out of losses, and all the rest goes to converted. This kind of crystallizes, at least for me, it crystallizes. Whoa, wow, now I can see why I need to lower my slip. Because the converted power all is done by 1 minus S. All the losses are a function of the slip. So again, hopefully this really crystallizes the point of why you want this machine to operate as high speed as possible, or as close to synchronous speed as possible. Remember, the motors we have in lab were only 1670. Those aren't designed to be efficient motors. Those are designed to be a little more robust. But when you get out in industry, and we looked at some nameplates, it wasn't that uncommon to see 1755, 1787. Well, we can take a look. Let's see. See if we can find a decent size nameplate. Let's go to a 500 horsepower motor nameplate. .500 horsepower motors are not that common. This is an oldie. See if we can make out the speed. This one is actually not an induction machine because you can see it has field amps. See, it's a direct current motor. So this is not even an AC motor. So this is not a good one for us. Let's see, is this a good one? 2300 volts, 3-phase. RPM. How many poles does this machine have? 2. Look how fast it's operating. Only has a slip speed of 25 RPM. And this looks like it's been fairly used and abused motor, right? When the nameplate's that dirty, it's had some tough times. So anyway, yeah, operate at really low values of slip.
I think you explained this before, but why do they put like 3575 instead of 3600?
Because this is the actual full load speed of the induction motor. This is what it operates at when it provides 500 horsepower operating.
So that's determined through just like testing it, and that's how they get that
But
value.
that's part of the design. So we know we can't run this at 3,600 RPM because
Yeah.
our slip would be 0 and we would have no, we'd have no rotating field on our rotor. So this can't be at 3,600 RPM. But what it's designed to do is you have losses you're trying to reach, and you're trying to make a motor that's relatively inexpensive and deliver the customer application. The customer said, I need a nominal speed of around 3,600 RPM. So GE has said, if I can get this to 3575, produce 500 horsepower, I don't need as much copper in my rotor circuit, so I can make a slightly cheaper motor. So it benefits them to run this at a higher speed because I need less copper on my rotor circuit. That means I need less weight, less bearings, or less heavy duty bearings, et cetera, et cetera. So this is a design parameter.
Gotcha.
But 500 horsepower is getting to be, that's a decent sized motor. Anything, if you in your professional careers come across anything that's probably over 50 to 100, that's getting to be a pretty big motor. I'm not saying they don't exist. I've specified 1,000 horsepower motors, but that's atypical. And this motor here, 500 horsepower, now you're starting to deal with medium voltage application, 2,300 volts. It's not a huge deal to get a motor started that can run like that, but you've just changed the operating facility. Most industrial facilities want to keep everything at 480 or less. Why? Because you don't need any special training. You get medium voltage, now you got to have special equipment, you have to have special training. You need more sophisticated electricians to test and more sophisticated operators to manage that equipment. Because death is a lot more serious when you're dealing with medium voltage. When you operate a switch, like you see if the Amera folks, I'm sorry, Versant folks were out doing work, you saw them with hot sticks and bucket trucks. The bucket trucks are insulated to 1,000,000 volts and they get 8-foot hot sticks that are insulated. They're as far away from the primary line as possible. But a few years ago at my house, we didn't have any power and they were out there on a 240 volt circuit and the guy was with his leather gloves just doing it. You could see sparking all along and he's just like, yeah, it's 240 volts. You know, you can get shocked with that and it doesn't really hurt you all that much. But medium voltage, most people won't touch it. Most people won't even go in their circuit breaker panel, which is only 120, 240. But once you start pushing medium voltage, and then you get higher arc flash energy. And we've talked about that in this class, but arc flash is, that's how you die if you're an electrician. You don't get, most of the deaths from electrical issues aren't from shocks, they're from fire. Because you get an arc and that has a lot of energy. And what happens when you see a bright spark? Your natural instinct is to go, take a big gasp of air, right? You just sucked in 35,000 degree air, which probably doesn't feel very good. Anybody here a smoker? Supposedly that burns your lungs too when you take those first couple of puffs, but I've never smoked. Okay, so questions on that stuff? Because again, understanding power flow is pretty useful. I didn't show the power flow for an induction generator because they're pretty unique. If you do come across induction generators, you're probably doing wind turbines. Okay, anything that's a variable speed, you might see those applications. Otherwise than that, it's almost always going to be a motor. Okay, so here's the stuff with torque versus power. We did maximum power transfer. So now we just have a simple series circuit. And those are the equations we talk about that we talked about a few minutes ago. Okay. So either write these equations down. Make sure you write also these, because you need those to figure out what the Thevenins are, or be good at MATLAB and run the number of settings. You do have MATLAB code, which you're welcome to use, but again, you can't just say the results are here. I'm not seeing if you're a good MATLAB programmer or good at reusing MATLAB. I want to see you understand the material. So if you do it on paper and pencil, show me your work, and you just say, just like your calculator, right? You can do a bunch of stuff on paper and then you come back with results. I don't actually see that your calculator results were correct, but but you show me your work before you use your calculator. MATLAB is the same thing. Okay, you shouldn't be using MATLAB for anything more than a calculator. So that's our max equations. Again, it's based on Thevenin equivalency. And when we did some comparisons, we found they were pretty close, right? There were some discrepancies between our sort of brute force MATLAB approach versus our Thevenin equivalencies, but they were generally, only 1% or so off. So that was a pretty good approximation. And then we saw that our slip, where our max slip occurs, is directly dependent on R2, but our max torque is not dependent on R2. So manufacturers, the way they get different operating characteristics is they adjust the value of R2. And that's how you get different NEMA design characteristics. NEMA, when I say NEMA, it's NEMA MG1, which is their motor generator standard. They've had that for 100 years. And if you want to learn more about, the exacting specifications, like a motor, we didn't talk about this, but if you go back to the motor, let's see if it says there should be a frame size. Right here, 509 LS. That's something that NEMA MG1 has come up with. And if you pull out a 509 LS, the standards for it, it'll tell you all the dimensions, like how far the feet need to be spaced apart, the shaft, where the shaft comes out relative to the feet position. There needs to be a keyway in the shaft. It has very exacting instructions. And that's because GE made this 500 horsepower motor maybe 20 years ago. What if you need to replace it? Well, if I order a 509 LS frame, I should be able to one-for-one swap it. And that's because you can't have too many custom applications because nobody could change things out. So it's basically saying, I don't know, I have a size 11 foot or something like that, right? It's pretty consistent in the US at least. I don't know if this applies in other countries, but in the United States, if you have a 50 horsepower motor that is failed, you can get all the same information here. Just make sure you match the frame size and you should be good to go. So that's why I said the options are do the loop equations either way. And then we did testing of the motor, which was very similar to our tests for in our transformer. We had the no load and the full load tests. Remember the data sheets we looked at? In a induction machine, we had to add one more test called the DC test. And the DC test, we needed to tease out the value of stator resistance. Everything else we were able to get with our blocked rotor, which is essentially our short circuit test. And this is our no load test. And this table over here. Okay. If I tell you a NEMA design and you don't remember, just make them the same and just make that as your assumption. Say, if it's a design B, just say, I don't remember if it's 0.4 or 0.6, just make them the same. So you don't need to worry about that in this table. So what I'm saying is, I either will give this to you or just say they're the same. Just say they're both half of XLR. Okay. So our DC test gives me R1. Our blocked rotor test, remember our slip is going to be equal to 1. So if we go back over here and our blocked rotor test, this is going to be equal to 1. And we're going to generally apply a low frequency. Well, let's go back up over here. If we can see it easier over here. So what we have, this is a low value relative to this. So everything is going to be here. So our block rotor test will give me a value for R1 plus R2 and JX1, X2. That's what the block rotor test does. The no load test will give us these values here, R1, JX1, JXM. Because we can directly calculate R1 in our DC test, we never use our no load test to calculate R1. We just use it to calculate X1 and XM. R sub C we can't really get. That's almost impossible to get. So under those tests, we have those values. And then the last thing you need to do is figure out the ratio for X1 and X2. So we would go ahead and maybe it makes sense. Instead of doing the block rotor test, the no load test, do the block rotor results first. You'll figure out R2 directly. Then you can get X1 and X2 as a ratio. So then you have all those parameters. And the last thing you do is do the no load test, and then you can pull out XM. So a good order would be to do number one, to get R1, then to do your block rotor test, which would be to get, R2, and then X1 plus X2, you can get those. And then in our no load tests, you're gonna be able to get XM. So if you follow in this order, 1, 2, 3, you won't have to jump around so much when you do your calculations. Excuse me. And I think the last topic we talked about is induction motor starting is still an issue. When we start a big load, that really drags down our voltage because the current is anywhere from 5, 6, 7, maybe 10 times what the full load current is. When that current is flowing through a transformer or a line, you can get a pretty serious voltage drop on that line. Enough so that the lights will dim. And if you have a contactor that's being powered from the incoming voltage, that contactor could drop out. The general rule of thumb is that the voltage is less than 90%, your contactor will drop out and then your motor no longer is allowed to start. You're gonna go back and hit the start button. So at that point, you would have to go in and figure out how to get the thing to start. One of the things you can do is a reduced voltage starter is an auto transformer, or you can put a VFD. And it just depends on the application. If you've got a little more money, you're better off to go with a VFD. They're really reliable and you can get the speed control you want, which usually means a more efficient operation, but they're more expensive. An auto transformer is very inexpensive. It adds a small cost to the unit and it doesn't really affect the efficiency over the long term. But that was our KVA code. So you're just going to pull that out of the table. And I didn't include the table. I would tell you the KVA code that you'd have to do the calculations. I'd give you the range essentially. And those are the test questions, the specific test questions. There's only 3, but there's going to be lots of steps to get there, kind of like the homework. So, the first one is determine operating parameters, which means given a DC short circuit. Nameplate data. So figure out slip, figure out power losses, that type of stuff. Then if you're given motor that you're measuring the current, calculate the power flow, including any losses. And finally, if you've got DC block rotor and no load tests, be able to calculate the equivalent circuit parameters. Okay, I've been babbling for an hour. Questions? Yes, sir. The KVA code? Yeah, so that code letter, if you remember, it's a KVA code, which tells you the number of KVA for nameplate horsepower rating. So if I need 5 KVA for nameplate horsepower, that just tells you I need to multiply. So this is just an inrush code. So that tells you that's a starting KVA or starting KVA code. So if I have 100 horsepower to start, I need 5 KVA times 100 horsepower or 500 KVA to start. So I calculate my actual starting current based on that factor of 5. Okay. How about TV land? This is always a tough time as a teacher and as a student because you all are fried. You're done, right? But the finish line is so close. And if you've noticed, we did slow down a little bit towards the end of the semester. I'm sensitive to that fact, so that's why we haven't had lab for the last 2 weeks. I don't know yet. I'm trying to arrange to go to a tour, but a lot of it depends on production. They don't want 20 people wandering around the production floor. So they're seeing if it's a cool place to go to AC Electric, but they've been less interested in hosting us because it's just they're swamp busy. They don't have the staff. It's just like the rest of the world. They don't have as many people. So they have people working gobs and gobs of overtime and 20 people getting a tour for 2 hours. It's a lot for them. It's a big commitment, but it's a wonderful tour. You really get to see a lot of the motors and generator stuff in this facility. And it's amazing to see. I mean, one time we were in there and they had just brought a motor off a truck and literally the guy takes out a power washer and starts washing it. And all the students like, oh my God, you're gonna blow that thing up. You can't get water in an electrical one. He's like, is it plugged in? I'm like, no, it's like, there's no problems here. We'll dry it out before we test it. Don't you worry. And they do. That's what you do. If you get something wet, you just dry it out, then you can plug it in. Well, so typically, if you watch them do the motor winding, at this facility in Bangor, some of them they will make there, but most of them they'll purchase because it has like a very specific geometry, and it's all separated, so it's magnet wire, and so it has a low, insulation around it, and then they have paper to kind of separate different phases. And then what they do is they set it in these slots, and now what they do is they put it into a special oven / vacuum chamber / mixing thing. So they put it in there, they heat it up to make sure all the moisture's out. You heat up something to 150, 200 degrees, that's well above the dew point. If you give it enough time and pull a vacuum on it, all the water goes away. Then they they throw in it's a resin that is a liquid resin, and it's an insulated one, and it's warm in there. So this resin flows through. And then what they do is they literally will pull a vacuum. You pull a vacuum on it, so all that resin gets sucked into the windings. If you just pour it on there, it doesn't easily get through. But when you pull a vacuum, it forces it through the windings. And then they gradually let it cool. And now you have a really solid insulation on these wires that can handle high temperatures, and the wires don't move. They kind of locked in position. And so that's it's a hybrid oven / vacuum impregnation the resin mixture. It's all kind of done in one step. It's a pretty interesting process, but that's how transformers, if they're dry type transformers, it's the same process how dry type transformers. If it's the best transformer is an oil filled transformer. So what they do is they put paper impregnation and they kind of hold it in position. So there is a little bit of vibration, but nothing like in a motor. And they just stick oil around it. And then the oil circulates. So transformers are more efficient because the oil, when it gets hot, natural circulation, the hot oil goes away and you've got coal or cool oil thereby. So the resistance gets to be lower. So oil filled transformers are much, much better, last longer. But some places you can't have it. Like if you're near a river, you probably don't want 1,000 gallons of oil spilling into the river. Even though the oil in a transformer is biodegradable, it's literally just plain old vegetable oil with some added resins and stuff in it to make it a little bit better. But it's all biodegradable. And anybody thinks that a transformer is going to blow up, it's basically like diesel fuel. Anybody ever start a fire with gasoline? It just explodes. Try it with diesel fuel. You pour it on and it's just like this low, that's the same thing. Motor oil, I mean, it will burn a long time, but it doesn't explode. It doesn't give off the vapors. So that's why electrical fires, they happen because it is flammable, but they do have some flame retardant additives in there. But you don't want oil going all over the place, because even though it is biodegradable, it's still a pain in the butt. If you have a substation, you've got oil all over the substation, you got to clean it up because it's just not practical to work. So they do have containment structures and fire suppression systems. You don't need as many fire suppression systems as they used to because the oil is so flame retardant. It's pretty good stuff. But oil can't work on a motor, right? Why? Because it's got to spin. Doesn't work so well when you have oil in there, right? Spinning around, you have centrifugal force. Eventually you would move away from the winding, so it's just not practical. The stator windings, you could have oil, but I've never seen a motor that has oil around the stator windings. They may exist, I haven't seen them. And I've seen a lot of motors. When I was at Maine Yankee, I was there for a year crawling around, and they must have had 5,000 motors. So really saw a lot older stuff, but the technology really hasn't changed. Okay, any questions? Well, if people would be so kind, if they could give feedback, because one of your classmates was very kind to provide some feedback on this, so unless they want to provide their name, I don't feel like it's professional to say that, but if you can provide feedback on this to see if it's improved or made worse, it's not to put down on them, but some people like a lot of detail, some people don't. I talked to a student the other day, they said they skim these, it's too many words for them, so it's a balance, right? I mean, when you're talking 6 pages of material, people tune out. So I try to be brief, but sometimes it's too brief. I don't know. So I got to wait, because I could just write stuff all day, but if you're not going to read it or look at it, it's not much of a point to do that. So any feedback is most appreciated. This is the first time I've done this in this class. I've never had these before, so that's why I'm hoping for feedback if people can provide those.
I know I personally find it better I'm a visual learner, and so just being able to see the schematics and formulas all put out, not in a very condensed way, makes I know it definitely finds it easier for me to remember.
Okay, thank you. You like the more detailed version?
Yeah. It still has the paragraph that explains what it is,
The narrative discussion?
and then it also is like, and then here it is the formula in the table is,
Yeah. Well, one of the ways I can do this is I can have no narrative discussion and just put equations. But to me, I worry about that because if you just look at equations, you don't necessarily understand what you're doing. I try to give a little bit of discussion. And when I do these, it sounds, I know this stuff pretty well, but this is how I would write it to myself. I'd explain it to myself so I'd understand it. So I would encourage you, when you're looking through this stuff, explain it to yourself. When you put it in your own words, it kind of makes that link. You have all these equations, but until you put it in phrasing or terminology that makes sense to you, it's not going to be a lot of success, in my opinion. But that's just how I learn. Like Ryan said, he's a visual learner. I don't learn that way. I have to write it and explain it to myself. That's just how it works for me.
I'm also kind of a visual learner, but I like to have the writing so that at the very least I can go through, I can like double check. And if I can read through it and understand it, then I know that I've got it.
Okay. So both. It's not too
Both
long.
for sure,
then.
yeah.
6 pages is a lot. And a student
Well,
was
it's a
honest
lot,
with me
but
the other
we
day
can
and said,
skip
yeah, I
through
skim
and
it. I
yeah,
skim
we
it.
can skip through and make sure we just want, like, we just get the stuff that we're after. If it's too much for us, and then if it's not enough, then there's plenty there.
Yeah, there's plenty there. Pat, you were saying, sorry.
Oh, I just thought 80% of that.
Okay,
I never know.
More is better than like small. Like some parts like I don't remember, so it's helpful to have a lot of paragraphs to like read it through.
okay. Good. Well, I'll have to do this for 422 next semester, right? For those of you who are taking it, so. Okay, any questions? I will be around tomorrow and I'm giving an exam in my other class, so I'm going to be in the classroom down the way. So if you want to have questions during the lab, just kind of peek in. It's the EET321. That's why I'm giving the exam. So I'm just proctoring it. But if people have questions, you should be able to, well, actually, you can't Zoom me because I'll be in a Zoom session. But if you want to knock and just come in and check or just do it quietly, I don't think it'll be an issue. I'll mention it to the students. All right. Have a great day, everyone, and see you on Thursday for sure. Take care.
Thanks, Paul.